Now we are in a position to say something about the finite, all the finite subgroups of this SO3. So the question is something like this. We have a group G, which is a subgroup of SO3, but it is finite, so the order of the group is a finite number. And the question is, what are the possibilities? What can we expect for the possible groups in there? So I'm going to answer that, but of course this is a little bit complicated issue, so as a result I'm not going to give any proofs. I'm just going to state the results, at least for the most complicated part. So, but before that, let's just introduce this terminology. We say that for a given group, for a given rotation group basically, we say that a direction M is an n-fold rotation axis if we have a rotation around this axis, which is basically by an angle 2 pi over n, right? And of course, all the other rotations around this axis just have angles which are integer multiples of that. So therefore, this 2 pi over n is basically is the smallest angle of rotation. So basically, let's just give a few examples. So if we have a twofold rotation, then there are these 180-degree rotations around this axis. So that's just one of the rotations. If this axis is threefold, in that case, we have like, apart from identity, we have a 60-degree rotation. Sorry about this. 120-degree rotation. 120 degree, this 1/3 of 360, or a 240-degree rotation, or you can describe this as, if you want, minus 120. And if we have I don't know, let's say fourfold rotation axis, in that case the angles might be 90, 180, and 270 degrees. So there are three non-trivial rotations in such a situation. So in any case, a description of the rotation axes of a group actually gives a lot of information about the group itself. So as a result, we would like to describe the group by just counting all of these rotation axes. So one of the important things in here is that that's one of the things that we are going to come out. So we are going to actually use a lot. If you remember the conjugacy relationship, a rotation around the axis M by an angle theta, let's say, if you just think about that rotation, we know that this is conjugate to a rotation by, if, I don't know, let's say that S is an element of the group, let's say. Therefore, this rotation is conjugate to S applied on theta M. So therefore, this is theta times S applied on M. So this kind of tells you that if M is an n-fold axis, so if M is an n-fold axis and S is an element of the group, let's say it like that, in that case, S applied on M is also an n-fold axis. It's basically the conjugacy relationship. So you can also analyze the conjugacy relationship like that. So that's true for any kind of a rotation, because any kind of an S in here. So you can use this S for a similarity transformation to actually, in a way, convert a rotation around M to a rotation around SM by the same angle. Right? You can think of it like that. So in any case, so let's then come back to our original problem, right? G is a finite subgroup of SO3. What are the possibilities? One thing is this. Perhaps G is a rotation, but it's just a rotation in a subplane, a two-dimensional plane of this three-dimensional space. So as a result, in that respect, G might be considered as a rotation in two dimensions. So therefore, it can be considered as, I don't know, a subgroup of SO2, for example, which we have covered. So it appears that we have said that, of course, there are these subgroups of O2, which can be either the cyclic group Cn or the dihedral group Dn, but the dihedral group actually contains some reflections in there. But it appears that at least there are these special cases where our group, our subgroup in 3 dimensions, can be one of these. So as a result, let's just go over these. So there's the situation in here that where the group G might contain only a single axis, a single rotation axis, and this might be an n-fold axis. So this basically corresponds to the thing that I have described in here. Basically consider a plane which is perpendicular to that axis, so call that as P. So therefore we can think of this group as rotations of the vectors within that plane. So that basically implies that any vector in here would be converted to another vector by just rotations within that plane. So as a result, you can then think of this group as a subgroup of SO2, in which case we know that this group is basically the cyclic group. I'm just going to use equality in here instead of isomorphism, but I'm essentially talking about the structure of the group. So some of these notations are used frequently to describe the structure of the group. So this is a group where the group is cyclic, so it's abelian. We know the representations of these, so as a result, we are not going to say anything about it. Next case, there is a situation where the group G is isomorphic to the dihedral group. So this is a situation like this. Let me express it like that. This is a situation where we again have a single n-fold axis, and there are many two-fold axes. So the situation is like that again. So we have a plane in here. So let's say that M is the n-fold axis, right? So we just have a single axis in here. We consider the plane perpendicular to that axis. And somehow, if I have a two-fold axis in here, let's say this one, for example, in that case, you can see that there's a 180-degree rotation in here, which will map this axis M into minus M. And so therefore, this is a possible way of transforming this axis into itself. So as a result, this is kind of a load in here. And so you can also see that if this is a two-fold axis, then by doing any kind of an, 2 pi over n rotation around this axis, you can map this two-fold axis to another two-fold axis like that. In any case, let me just cut the story short. In here, of course, all the operations are just rotations. They don't contain any reflections. So we don't have any reflections in here. So in that respect, the group is not has nothing to do with a subgroup of O2. There are no reflections in here. However, if you just look at the effect of these twofold rotations on vectors in this plane, just remember that this twofold rotation, for example, it basically maps this vector M into minus M. It maps in M into minus M. And therefore, it also maps a vector within the plane into the negative of itself. But it maps this direction, let's call this as W, into itself. So as a result, within the plane, it looks like the effect of that twofold rotation is just like a reflection, right? But it's not a reflection, of course. In 3 dimensions, the operation is not reflection, but in 2 dimensions, the effect actually amounts to a reflection. So as a result, in here, this kind of a situation, we get a situation where this group is isomorphic to the dihedral group that we have seen before. So again, in here, I'm going to write this thing down as an equality. So as a result, we have these 2 cases, which is just a repetition of the possibilities that we have seen in 2 dimensions. So that group might be a subgroup of SO3, might be the cyclic group, or the dihedral group. In both of these cases, we are essentially talking about the transformation of vectors in a two-dimensional plane to vectors in the same plane. Okay, so it appears that in 3 dimensions, of course, there are more possibilities, but just a few. So it appears that there are actually 3 more possibilities in 3 dimensions. There are 3 more groups that we can actually count. And the whole result can be expressed like this. So this is one of the things that I'm not going to prove, because this is a little bit more complicated for us. So basically, if G is a finite subgroup of SO3, then the possibilities are that can be either the cyclic group or the dihedral group, things that we have seen before, or it might be the symmetry group of one of the 5 Platonic solids. So I'm going to describe these. But there are actually 3 such groups. So these are shown by the symbols curly T, curly O, and curly I. Curly T is the symmetric group of tetrahedron as the shape. Curly O is the symmetric group of an octahedron, but it's also the symmetric group of the cube. And I'm going to explain why the symmetric groups are the same. And curly I is the name given to the symmetric group of the shape icosahedron and dodecahedron. So these are shapes like that. In any case, let's see what these Platonic solids are. These are actually known from ancient Greek, so that's why the name is given like that. It's called Platonic solids. That they are special shapes where all the faces are regular polygons. But the shapes can be considered as the 3-dimensional analogues of regular polygons. So these are called polyhedrons. But these 5 special ones have this highest symmetry, and so as a result, the symmetric groups of these objects somehow also appear as the special symmetric groups. So I'm going to describe them. So there's a different shape in here. I'm going to also do some drawings on some of these shapes to describe something else. But let's just say a few things. So this hexahedron is essentially a cube. This is a cube, right? And we are saying that somehow the symmetric group of the cube and the octahedron, they are the same. And also the dodecahedron and icosahedron, they have also the same symmetric group. To see this, of course, we have to see something about what we call as a duality transformation. So I'll just explain this on the cube. So, of course, to describe a polyhedron, we have these special objects. We have these corners in here, which we call as vertices, vertex. We have edges in here that connect 2 vertices, and then we have faces. So the number of vertices, for example, for a cube is 8. The number of edges is equal to, I need to count this, 12. And the number of faces is equal to 6. There's a famous relationship of Euler that says that the number of vertices minus the number of edges plus the number of faces is equal to 2. So that's in general true for all kinds of polyhedra, but we have nothing to do with this, so I'm not going to deal with this. In any case, let me use a different color in here. So an edge like this one in here can be considered as connecting either 2 neighboring vertices, you can think of it like that, or it can be considered as connecting 2 neighboring faces. So this face and that face, they are neighbors, so these 2 neighbors actually meet at that edge, right? So there's something, in a way, a dual function for each edge. So you can think of an edge connecting either 2 vertices or 2 faces. So the duality transformation is a transformation that actually changes the faces into vertices and vice versa. So it just changes these 2, and somehow changes edges into edges because of that. I'm going to describe how this happens. So let me first change the color of this thing to the original one, white color. So what we do is this. I think I'm going to use the red color in here. We just take a face in here like that and just mark the midpoint, the central point of that face. Okay, so what we do is, instead of faces, we are talking about the midpoints of these faces. So I'm going to mark this face like that. So I think I'm going to exaggerate. So as a result, the shape that I'm going to draw will not be a perfect one. In any case, since we have 6 faces, we have 6 such points. Okay, what we do is this. We now connect 2 such points with each other with an edge if the corresponding faces are already neighboring faces. So as a result, let me draw this thing in here. So these 2 points correspond to faces that are connected by they are neighbor with an edge. So therefore, I just connect them with an edge. So essentially, this edge of the cube is transformed into that edge of that other shape in here. In any case, so we know that each face is a neighbor to 4 faces for the cube. That means that these every point in here would be connected to 4 other points. So I'm just going to do that. So for the topmost face, I'm going to have these kind of connections. I think I'm not going to draw any dotted line. I'm going to draw some dotted lines. So as a result, this point, for example, will be connected with this one, with that one, and with this one, and so on. Let me just draw all the other ones. So okay. So as a result of that, we get another polyhedron. And since my shape has this perfect symmetry, whatever this symmetry operations that leave the cube invariant, the same operations are going to leave that shape invariant. So it appears that the shape that I obtain in here is the octahedron. So basically, duality transformation transforms cube into octahedron. So when it does this, of course, each face, each face is replaced by a vertex. So every face of the cube is the vertex of the octahedron. So octahedron should have 6 vertices. Which basically corresponds to the 6 faces of the cube. And each edge, of course, is somehow replaced with each edge. So therefore, the octahedron should have 12 edges. And it appears that, of course, I can also do the same thing in here. So the vertex of every vertex of the cube, I can think of this as some kind of a point which is neighboring to these 3 faces in a way. So as a result, when the faces are converted into points, this vertex would be converted into a face. So as a result, since the cube had 8 vertices, this will correspond to 8 faces of the octahedron. All right, so we can go back and see that this is the case. I'm just going to use a yellow color in here. So you can see that the cube had 6 faces. I think I'm going to use a color like that, blue, for example. The cube had 6 faces, whatever. So the octahedron has these 6 vertices. So I'm going to erase now. The cube has 8 vertices. I need to erase everything back. So therefore, the octahedron has these 8 faces. So let me not color all of them. So you can see that somehow there's a correspondence between the vertices of the cube and the faces of the octahedron, and vice versa. And of course, each edge should be related with an edge. So therefore both shapes have the same number of edges, right? So these two numbers are the same. Okay, so I can also apply a duality transformation to the octahedron, but what we are going to get is basically a smaller cube in here, which has the same alignment with this bigger cube. So I think I'm going to do this in here. So somehow if I take all the midpoints of the faces in here, so in that case the faces are of course triangles, so you can see that there are these 8 vertices. If I connect them, I'm going to get a shape like that. But of course, I mean, this is going to be kind of complicated in here, so I cannot do a justice with the geometry in here. But you can convince yourself that what you are going to get is a cube inside, right? So let me also erase all of these in here. So let's see if I can do that. Yeah, I can do this. So this then tells you that since somehow I can place an octahedron inside a cube and a cube inside an octahedron with a duality, their symmetry groups are the same, right? So therefore they have the same symmetry group. Okay, that's going to be the same for the dodecahedron and the icosahedron. So I'm just going to count the numbers in here. I'm going to use a white color in here. So dodeca means 12. So dodecahedron is essentially a shape with 12 faces. The number of edges I forgot to count, but I'll say something about this. Yeah, let me quickly do this. So since the number of faces is 12 and each face is a pentagon, so that means there are 12 times 5 edges. That means 60, but every edge is shared between 2 faces twice, so therefore there are 30 edges. How many corners? I need to count them, but let me quickly write this thing down, that the number of vertices of dodecahedron is 20. Icosahedron has 20 faces. I can just write it like that quickly in here, so you can actually, the number of faces of one of them is basically the number of vertices of the other one, and so on. So these two are duals of each other. So dodecahedron and icosahedron, they are also dual to each other. Again, because of the same reason, these also have the same symmetry group. Same symmetry group. So the symmetry group of the icosahedron is called I. The symmetry group of the octahedron and the cube is called O. Tetrahedron is the self-dual of itself, so therefore this is somehow by itself. So let me also talk about this. So if we have a tetrahedron in here, like that, it basically has 4 faces with 4 corners. Let's talk about this midpoints of each face. So this triangular face has this midpoint or central point. This triangle has this point. So this triangle that we don't see has this midpoint, and this one is that midpoint. So if you just connect them all, you're going to get a shape like that. It's actually a tetrahedron which is somehow upside down. You can think of it like that. Again, it is smaller, but you're going to get a tetrahedron nevertheless. So as a result, it's the dual of itself. So as a result, this is basically a special shape. So you can see that there are actually 3 symmetry groups, and the previous theorem basically tells us that there are no other kinds of subgroups that we can find in nature, or in mathematics basically. So in nature, of course, we actually meet all of these symmetry groups. The icosahedron is the symmetry group of what people call is C60 or Buckminster fullerene. This is a very special molecule formed from 60 carbon atoms. It's actually a shape that is called as truncated icosahedron. So it's actually it's a little bit more complicated shape than an icosahedron. It has actually 60 vertices. Each vertex has a carbon atom. So as a result, there is a molecule having that symmetry. So as a result, these are not just some strange groups. So we have some kind of a system that actually has this symmetry. So there are these cubane molecules that have this cubic symmetry. There are these kind of molecules. We have the methane molecule, the CH4, that has the tetrahedron symmetry. But in all of these, of course, there are also these inversion. Operations that also involve inversion, which makes the symmetric group a little bit larger than these. So it's not just these. But in any case, at least for the proper rotations, these are the symmetric groups. The group O, this group is also important for solid state physics because a lot of materials, like the semiconductors, for example, most of the semiconductors that we work with have a lattice structure that has this cubic symmetric group. So as a result, this symmetric group is also very important for some other respects as well. So as a result, we just meet some of these groups a lot in applications. We need to say a few other things about the conjugacy classes and things like that, but I don't want to do this. I just want to say something more about the symmetric group of the cube. So the name of the symmetric group is of course O, but you can actually see some of the operations in there. So I'm just going to draw a cube in here, and with a different color, I'm just going to draw a few of the rotation axes. So that's the symmetric group O. So I'm going to start with a yellow. I think this is the symmetry with the let's say it like this. This is a fourfold axis in here. So this is an axis that passes from the central point of the cube, and we have a axis like that. So there's a fourfold axis in here, which basically converts each square face to itself, and of course these square faces to the other ones as well. So there's a fourfold axis like that. So therefore there are these 90 degree and minus 90 degree and 180 degree rotations in there. If you're talking about conjugacy classes, of course, a 90 degree rotation having this symmetry axis is conjugate to another 90 degree rotation having a similar fourfold rotation axis. So for example, there's a fourfold axis in here that passes from this face, for example. So as a result, a 90 degree rotation around this axis is equivalent to a 90 degree rotation around this axis, or minus 90 degree rotation around this axis. So you can easily convince yourself that this is the case. So let me erase this. There's this one of the axes in here. Surprisingly, I find it very surprising that this shape also has a threefold axis. So basically, you just think about a body diagonal. So you just take this corner, one of the corners, one of the vertices of the cube. You can see that there's actually one special corner in here which is just diametrically opposite to that corner. You just consider a line that passes from these two vertices. So as a result, we get a line in here. All right. So you can draw some similar lines in here. So for example, for this vertex and for that vertex, there's also a line in here. In any case, this is a threefold axis. It's a threefold axis. Okay. And then there's a twofold axis, so I'm going to use a green color for that. So I think I'm going to do this. So I'm going to choose the midpoint of that edge and the midpoint of that edge. For this one too, the axis passes from the center of the body center of the cube. So there's an axis like that. goes inside. I think I should use the dotted lines for the inside ones, right? So this is a twofold axis. So as a result, this group O therefore has symmetry operations whose order is 4, 3, and 2. And basically you can relate all of these operations with the rotations around these axes. So by using, of course, these axes, you can also identify the conjugacy classes. I forgot how many conjugacy classes in there, but I believe that all of these threefold rotations, 120 and minus 120 degree rotations, they are conjugate to each other. All of the 90 degree rotations around this fourfold axis, plus 90 and minus 90 degree rotations, they are conjugate to each other. All of the 180 degree rotations around the fourfold axis, they are also conjugate to each other. And finally, all of the 180 degree rotations around these twofold axes are also conjugate to each other. But the 180 degree rotations around these twofold axes are not conjugate to 180 degree rotations around this fourfold axis. There is also the I density, which is only conjugate to itself. So if you just consider all of these possibilities, you can then identify all the conjugacy classes in there. And then, of course, once you identify the conjugacy classes, then it's a very simple exercise to construct the character table. So you then know how many irreducible representations are there. You know the order of the group. Again, this is something that I forgot, but you can actually easily count them. So as a result, by using this, you can find dimensions, and then by using some other ideas, you can also find the other characters and things like that. Right. So without doing any concrete examples, and then I don't need to do any further discussion in here. Okay, so then let's finish it in here.